Go ahead and do an example problem for the air standard diesel cycle. This problem says that an air standard diesel cycle has a compression ratio of 16 and a cutoff ratio of 2. And at the beginning of the compression process, the air is at 95 kilopascals and 27 C, accounting for the variation of specific heats. So this problem right away, right, we can assume, of course, that air is an ideal gas, but in this problem is telling us to solve it for variable specific heats. So that's going to change how we do things compared to the prior example problem, the Otto cycle that we did. So accounting for the variation of specific heats with temperature, determine three things: the temperature after the heat addition process, the thermal efficiency, and the mean effective pressure. So first things first, let's go ahead and draw a PV diagram. So starting at state 1, state process 1 to 2 is isentropic compression. Process 2 to 3 is constant pressure heat addition. Process 3 to 4 is isentropic expansion, and 4 to 1 is constant volume heat rejection. So what we're trying to do first is follow the process lines in order to get the temperature after the heating addition process. So T3 is what it's asking for. That's what part A is asking for. Part B is asking for the thermal efficiency. So if we're going to go ahead and compute the thermal efficiency for any heat engine is 1 minus Q out over Q in. So we're going to have to get some first law analyses going for process 2 to 3 and process 4 to 1. If you recall, Q out is going to be equal to delta U, and Q in is going to be equal to delta H. So I'm going to have to get the enthalpy at state 2 and state 3, and the internal energy at state 1 and state 4. So let's go ahead and get started. State 1. I know my temperature is 300 Kelvin, and I know the pressure is 95 kilopascals. And I'm trying to analyze process 1 to 2. So I want to go from state 1 to state 2. Now if I go back and look, it will show that that is an isentropic process for an ideal gas with variable specific heats. So if we remember, to treat an ideal gas, in order to find the state change of an ideal gas undergoing an isentropic process with variable specific heats, you can use one of these two correlations using relative pressure or relative volume. This problem, we're going to use relative volume because the problem gives us volume ratios, right? If you recall, the problem gave us that the cutoff ratio, nu3 over nu2 is equal to 2, and the compression ratio, nu1 over nu2 is equal to 16. So it would make sense to go from state 1 to state 2 using the compression ratio. So if I go back to state 1, I'm going to go ahead and find, using table A17, right, that's the ideal gas table, I go to 300 Kelvin, and I find that my relative volume is 621.2, and I find that my internal energy is 214.07 kilojoules per kilogram. So with that, I get my relative volume at state 2 also, and I can calculate that as 38.8. So then I can go to state 2, knowing my relative volume of 38.8. I can go back to the ideal gas tables, and I can find that T2 is 862.4 Kelvin, and H2 is 890.9 kilojoules per kilogram. Next, I'm going to go ahead and follow the process line from state 2 to state 3. So if you recall, process 2 to 3 is constant pressure, and that is for an ideal gas. So P nu is equal to RT. I'm going to put on one side of the equation everything that's constant, and I'll put on the other side of the equation everything that is changing. So if I do that, I can find T2 over nu 2 is equal to T3 over nu 3. And I can solve for T3, which is equal to nu 3 over nu 2 times T2. Just so happens that nu 3 over nu 2 is the cutoff ratio. So I can get that T3 equals 1,724.8 Kelvin, which happens to be what part A of the problem is asking for. Now what I'm going to do is, for state 3, knowing the temperature, I can find H3, and I can find the relative volume at state 3. Why? Because process 3 to 4 is another isentropic process. So now I go ahead and I analyze process 3 to 4. Again, this is an isentropic process for an ideal gas with variable specific heats. So that would tell me that nu 4 over, relative volume 4 over relative volume 3 is equal to nu 4 over nu 3. Nu 4 equals, relative volume of state 4 is equal to nu 4 over nu 3 multiplied by the relative volume of state 3. Now, how do I quantify nu 4 over nu 3? If you recall, the cutoff ratio is nu 3 over nu 2, and the compression ratio is nu 1 over nu 2. Just to show you, R over the compression ratio over the cutoff ratio is equal to nu 1 over nu 2, that divided by nu 3 over nu 2. This simplifies to nu 1 over nu 3, and if you remember back, nu 1 and nu 4 are equal to each other. That's a constant volume process, 4 to 1. So that means nu 4 is equal to nu 1. I can go ahead and replace this as nu 4 over nu 3, which equals 8. So therefore, that relative volume at state 4 is equal to 8 times the relative volume at state 3. Therefore, the relative volume at state 4 is equal to 36.37. Knowing that, I can get state 4 using that relative volume. I can find that the internal energy at state 4 is 660 kilojoules per kilogram. So now I can go ahead to part B, solve for the efficiency, Q out over Q in. So if I recall, Q in is during a constant pressure process, so that'd be H3 minus H2, and Q out is during a constant volume process, so U4 minus U1. You plug in your delta H's that we got from earlier, you get 1,109.7 kilojoules per kilogram. If you plug in your delta U, you get 445.6 kilojoules per kilogram. And if you plug those into the efficiency, you'll get an efficiency of 56.3%. And then lastly, for part C, the mean effective pressure with work net over the change in volume. You can go ahead and solve for this in much of the same way as you did for the Otto cycle, and you would end up with mean effective pressure of 676 kilopascals. Now again, the main part of this problem, guys, is following the process lines, making sure that you follow the process lines. So we started off at state 1. We ended up getting the relative volume and the internal energy. We followed from state 1 to state 2 for an isotropic process, got our properties to state 2, followed the process line from state 2 to state 3, which is a constant pressure process, to get T3 in order to be able to get our properties at state 3, and then follow the process line from 3 to 4, which is again an isotropic process, in order to get the relative volume so that we can get our internal energy at state 4. Plug in those properties to get our energy transfer terms, Q in and Q out, in order to get the efficiency.